Hello everyone, I'm Kalpani Ranasinghe. I'm here today to introduce you to SciFlow, a composable framework for scientific workflows on HPC clusters. We are a team of 6 people who represent the University of Colombo School of Computing, Sri Lanka. This is the outline of the presentation, starting with the background study, solution, architecture and functionalities, case studies, result and comparison, and the conclusion. Let's take a look at the motive behind creating this framework. We identified that scientists often face a major challenge when mapping their high-level conceptual knowledge to recent computational models. The complex interconnected tasks and massive amount of data involved in scientific work make such modeling even more difficult. These situations can be made less challenging through scientific workflows with HPC and parallel infrastructure. Workflows can be further enhanced by reusability, which can be achieved through separation of computation from coordination. Now I'm going to briefly outline the core concepts involved in this research. Programming flexibility in workflows. We can achieve this by separating coordination from computation of an application, resulting in pure control modules. Channel coordination in workflows. Control-driven coordination models can be used to construct event-driven workflows. Although several control-driven channel-based languages such as Rio exist, their implementation is largely conceptual. Communicating sequential processes is a viable alternative. The channels of a Go programming language are built in accordance with CSP model. Dynamic workflows. We can use channels as primitive connectors to model complex connections to create dynamic workflows. Parallelizing the execution to provide minimal user effort. Traditional MPI-like burden can be avoided by using implicit parallelism. This can be achieved using Python parallel scripting library Parcel. Scientific workflows gain simplicity, programming flexibility, and architectural expressiveness by using parallelism and channel coordination. So, SciFlow merges these two concepts to allow controlled implicit parallelism using Python, Parcel, and Golang. Diagram in the right shows the conceptual overview of the framework process. First, the composable computation modules are defined using Python. Thereafter, compute-intensive modules are parallelized using data and task parallelism techniques, and this has achieved through Parcel. The coordination model and dynamic decision points are defined via the control thread. It is written using Go programming language and may consist of different connectors. Finally, HPC configurations are modified and the framework may be executed on a defined platform, and this also can be achieved easily through Parcel. We just need to modify the configuration file in the framework and you can run it anywhere. So as a summary, a SciFlow workflow can be constructed by stringing together individual Python Parcel computational units coordinated by a Golang control thread using a concept called connectors. Let's take a look at the different connectors in SciFlow. This diagram depicts the simplest of connectors available in SciFlow framework, which is the sequence connector. The sequential connector is used in instances where the control simply passes from one component to another. When a computational module completes its task, a signal would be sent through a Golang channel to the control thread. The connector would then pass the signal to another channel based on the defined control logic, which would in turn triggers the next computational component into execution, also known as event-driven coordination. We provide the implementation of 7 such connectors, including those catered towards AND gates, OR gates, XOR gates, and loops. These are mapped to some commonly occurring control flow workflow patterns as well. The diagram on the left shows an abstraction of the core functionalities of SciFlow. Using the previously mentioned channel connectors, the user is able to connect computational components in a multitude of workflow patterns as suited to his application. The workflow displayed makes use of 3 types of connectors. One for sequential execution, another for splitting the coordination thread into parallelly executing modules, and one more for dynamic decision making. With dynamic decision making, the workflow could be automated to run a number of times parallelly with different parameters. Connectors can be used to select the best performing parameter set based on some performance metric. Based on selection, the workflow path would be modified at runtime to yield better quality results. With Parcel's implicit parallelism, we are able to orchestrate this entire workflow on any HPC resource. The scientific workflow applications SciFlow caters to make use of large data sets. Therefore, we use both data and task parallelism to improve computational efficiency as shown in the next diagram. The framework executes computational modules concurrently using the Golang control thread, thereby providing task parallelism. This proves extremely helpful in situations similar to hyperparameter optimization. Using SciFlow, the user has the ability to divide the dataset either horizontally or vertically as suited to emulate the data parallelism. We were able to deliver this functionality through the developed framework by integrating Parcel library. We successfully implemented 2 case studies using SciFlow in order to validate the design of the framework and its usability. Hyperparameter optimization was performed on the data analytic workflow as dynamic decision. The ease of finding the best analytical model was observed, and our aim was to predict social unrest events that happened in a specific country by SciFlow workflow and test how accurate the result is. We drew inspiration for this method from the paper Predicting Social Unrest Events using GDLT by Gala and Berg. The 2 source datasets we used were the Global Database of Events, Language and Tone (GDLT) and the Armed Conflict Location and Event Data Project (ACLED). These were combined to create the labeled testing database. We have acknowledged ACLED as the ground truth. Both GDLT and ACLED datasets follow different data preprocessing approaches before it combined. Then the dataset moves to the mining stage where hyperparameter optimization was performed on all of the mining algorithms. The resulting tree models from each of the 3 stages are then tested for the accuracy on testing dataset. The Golang control thread would select the best model and its parameters based on this testing accuracy. The workflow is said to be dynamic due to this path selection mechanism according to the results gained at runtime. Now let's take a look at how connectors are used in this case study. In every instance where a module appears after the execution of the previous one, the sequence connector is used. When it comes to the stage where 2 datasets merge, the control flow calls upon the synchronization connector. Then parallel split is called to replicate the integrated dataset into a separate branch for conducting k-means. Then the top branch goes through some other modules and comes to a point where it splits again with a multiple choice connector, which acts as dynamic decision point as well. The second case study, combinatorial optimization. Here we split the traditional TSP-PSO algorithm into three workflow modules. The PSO algorithm module was integrated with the loop connector to execute for a defined number of times. In our method, several PSO instances were created and executed parallelly using parser. Each of these instances would output one cheapest value. The control thread would extract the lowest cheapest value out of these. This solution, which corresponds to a cost and a path, is added as a new particle to the next round of the PSO instances to make sure the framework finds an even lower cheapest value. The rounds are synonymous with Golang steps orchestrated by the control flow. This approach is a new way of optimizing the PSO algorithm identified by the team. Typically, scientific workflows are represented as directed acyclic graphs. But with the second case study, we hope to explain SciFlow's unique ability to facilitate directed cyclic behavior. It also proves SciFlow's ability to handle a well-known and complex scientific problem. In order to determine the accuracy of the dynamic data analytics workflow, it was run on cores of a local machine. With SciFlow, the data analytics workflow was completed in 1 hour and 10 minutes. As the framework selected the best model for the final output phase was support vector machine with an accuracy of 63.1%. Without SciFlow's dynamic decision-making capabilities, the same model would have to be parameter tuned manually, taking more time. Also, there is no guarantee that the selected parameter set is actually the best. The accuracy of TSP is measured by comparing SciFlow's solution to a typical PSO algorithm, an ant colony optimization algorithm, as well as the optimal solution found thus far. In every problem, the cost obtained by SciFlow is much lower than the results of the traditional PSO algorithm. The solution value kept decreasing as the number of steps, or in other words, the loops increased. Therefore, we can conclude that with higher computational power, the framework has the potential to provide an even better solution. Resource utilization of a dynamic data analytics workflow was evaluated on threads of a single machine, cores of a single machine, and a 4-node cluster. Using Golang channel coordination slightly increases time due to what we believe to be communication delays. However, these would be negligible given a large enough dataset when considering the flexibility granted. Without implicit parallelism, the execution time increased significantly. Throughout this presentation, it was emphasized how merging several well-known principles could produce additional desirable features and therefore enhance the processes. SciFlow's fundamental paradigm, which we call controlled implicit parallelism, corresponds to this concept. Therefore, let me end by saying that through this development, we were able to provide programming flexibility and efficiency in a workload-dominated HPC environment. If you have any questions or comments, I'll be happy to answer them now. Thank you.